Any questions up to this point? All right, so we only have to concern ourselves with what? The numerator, right? We will have to consider the denominator when we figure out when this thing might be undefined. But we, right now, just have to consider the numerator. So I'll distribute, well, I'll just do this. So distribute through, we get 18 minus 2x minus x equals 0. Negative 3x, or 18 minus 3x equals 0. So what's our solution here? 6. Looks like 6 is a solution.
And then our restricting is going to be positive 9. Because if you,
For what?
for the denominator.
Okay, yeah, yeah, it's going to be,
Because if you go 9 minus positive 9, you get square root of 0. And then 2 times 0.
where does this not exist? That's what we're asking ourselves, right? So this would have the derivative, which is right here. Well, right there or here. I like looking at this one. That would not be defined where?
At positive
9? Do you all agree? 9? What about 10?
Yes, so anywhere greater than.
Yeah, so there's actually a lot of places this is not defined, right? Any time that this number here is more than 9, we're going to have a problem.
So would you say x is greater than or equal to negative, I mean positive 9?
Well, we have to actually back up a little bit. Slow down just a little bit. Look at the original function. Does it have a domain? It does, right? There's a domain restriction on this original function. I can't take the square root of a negative number, right? So when I come back up here and I look at this guy's domain, I know already that my domain has to be, oops, wrong way. And that's an important step. And everyone here needs to understand where that domain is coming from. Right? I could put 9 in here, couldn't I? 9 minus 9 is 0, and the square root of 0 is 0, and that's fine. Now, I can't put 10 in here. I can't put 9.1 in here. Can't have anything bigger than 9. I can put negatives in here, though, right? Yes?
It's negative infinity to 9.
Yes?
So anything smaller than 9 would be okay.
Yes.
Yeah, because you.
Like 9 would work here, right? 8 would work here? 7? 6?
Yeah.
Are you agreeing? Okay. And if I put a negative number here, like negative 5, I do 9 minus negative 5, that's 9 plus 5. That's okay. Square root of, that's fine. Okay? So this is my domain. Now, when I'm coming over here asking myself, where's the derivative not exist? I really can only be looking here. I'm only allowed to look here because that's the domain of the original function. Anything outside that domain, I don't have to worry about. So is there anything that's in here that would cause a problem with this? 9, just 9, right? Just 9. Because 9 would cause division by 0. So that's the only point. This number is in the original domain, but it causes a problem with the derivative. Now I go to a number line. 6 here and 9 here. I'll help wake you up. What next?
You gotta choose something to the left.
Okay, so go ahead. What do you want? 5? And 8 and 10. Good. And what am I going to do with these? Into the derivative, right? Okay, so those are going to go into the derivative. Now, here's the derivative, right? When you go to plug these numbers in, this is the point where you want to really make sure like your derivative is cleaned up as possible. So I'm going to take that and I'm going to clean it up even more. Just kind of rewrite my derivative here. My derivative, when I distribute that through, we already did that earlier. This was 18 minus 3x over 2 root 9 minus x. I think that's the cleanest version of the derivative that I have. And now it should be somewhat easy to plug these numbers in. 5. Let's go with 5. So if I plug 5 in here, I'm going to play that same game of just figuring out if it's positive or negative. 5 here is 15. 18 minus 15 is positive. Over 9 minus 5 is positive. Square root of positive number is positive. Times 2 is still positive. Everything's positive down here, right? What's a positive divided by a positive? Positive, okay. So I know that my original function here is going up. And then plug in 8. That one is done. So I better pick that up. He's going to come back in and Nas is going to fall and break his arm. Spurs are playing this weekend, huh? It's negative when you plug in 8? Or just on the top it's negative? So you plug 8 in here, it's negative on top. And then on the bottom, you should get a positive here. So that's going to be a negative, right? Okay. So F is going down. All right, we have a problem here. So 10, remember how we drew our number line and we picked these points and we had picked 10? And we really didn't say anything about it when we did it. But remember, the original domain of the function stops at 9, doesn't it? So that means you don't need to look over here. You can't look over here because of this. Which means really we only had one critical number. We tested on each side. You could say that we technically have tested to the left of 9, can't you? But this is all we need. We have a single local maximum. That's all we have here, right? We have no local minimum on this function. Is 9 what?
Is 9 not both the local and minimum? Like local and absolute minimum?
Well, we have to actually look at the endpoint. Okay, we have to analyze it. We want to plug the number. We're going to want to plug the number 9 into the function. Okay, we're going to want to plug it in, just like we're going to want to plug 6 in. We're going to want to plug in 9 because we can, right? We're going to say we have a local maximum, right? And we haven't really talked about this. We haven't had a problem yet where we're looking for down then up, right, for local min. But what if it just goes down and that's where our domain ends? What is that, right? I think that's what you're referring to, right? So let's first figure out where is it increasing? Negative infinity to 6. Okay? Where is it decreasing? 6 to 9, right? And what about a local max? That happens at 6, and what is the value at 6? 6 root 3. Whatever that is, it's an irrational number, but 6 root 3 is our local max. So I'm just plugging 6 into the original function. And then what about a local min?
Zero. Well, I mean, if you plug it in, you get 0, but I mean, it's obviously asymptotic. Can we take another number?
Is it asymptotic? What is happening here? What is happening? Our function exists this way, doesn't it? Like if I keep drawing it this way, there's picture over there. As I come in from the left to right, it's going up, 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 right? So if I turned around, it's going to be going down, 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 down. So the thing just goes down forever. Now coming this way, it goes up, 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 up. Well, I shouldn't say it goes down forever, but it's going down as I move to the left, yes? It goes up like this, comes over, there's our local max, then it comes down, and all of a sudden my graph stops, right? So that point should look something like this. Boom. The question is that a local minimum? Is it the lowest point near, in the little neighborhood near it? Well, near means, well, is that point's a local max, right? Because it's the highest point near it. Is that the lowest point near it? Well, yes, it is. Look, because you're only allowed to look this way. Because you can't look this way because that's not in the domain. So this is actually a local minimum. Because locally, it is the lowest point around. So we do have a local min at 9. But what's the value? 0. That's a little tricky, huh? It's because of that domain. I'll tell you something really, this is really like dorky, math dorky. I used to have an office mate. When I first started working out here, my office was in one of those portable buildings. Do you all know that we used to use those portables for classrooms? So I had this office mate. I won't mention who it is. He's not here anymore, but I still won't mention his name. He and I were talking, and he was such an idiot. He was, well, I mean, idiot like dork. He was telling me, he's like, you know, I'm going to tell my girlfriend, it was like near Valentine's Day. He's like, I'm going to tell my girlfriend that the love that I have for her as a function of time, right? So his love function for her. He wanted, now she knew some math, I guess, that's why he was going to tell her this. He was going to tell her that the derivative of that love function was positive for all time. Okay? So basically for t from the moment he met her to forever. Like, right? So what does that mean?
Love is greater than infinity.
Well, his love is growing, right? As time goes on, it's growing and growing. And I told him, I said, you know what? You're sick, first of all. And then I told him, I said, I don't think that's very impressive. Because, look, let's say this is time. And let's say you have a horizontal asymptote like this. And let's say you have a function that started, let's say at 0, because he didn't know he loved her in the beginning. So as soon as he met her, the love started to grow. And does this function goes out forever, and it's asymptotic, which means that it's approaching this number. This function is always increasing, isn't it? It's always increasing. You go out, it's going to go up a little bit, but there's an upper bound. You have an upper bound. So I kind of blew his whole thing, and I said, this doesn't mean anything, because you could have a horizontal asymptote of like 50% of love. You know what I'm saying? Like, so if she knows any math, she's going to realize that doesn't really mean a lot. Like, you had good intentions, but so we had to modify the conditions here a little. He had to add a little bit more to this to take out the asymptote. Sick, isn't it? There's a simple way we could fix it. He just needs to make his second derivative also positive. Because the second derivative, and this is what we're going to talk about next, the second derivative tells you something about the graph also. So the first derivative tells you if you're going up or down. The second derivative tells you about the shape. The shape is the shape of your graph is one of two things. It's either what we call concave up, or the shape of your graph is concave down. All right? There's an easy way to tell whether or not it's one or the other. This happens when your second derivative is positive. And this always happens when your second derivative is negative. So first derivative tells you up or down. Second derivative tells you concave up or concave down. So look at that graph over there. This graph right here, the first derivative is always positive, right? But the second derivative is what? Negative, right? So concave down. That's how you get this asymptotic feature. But if I tell you that the second derivative has to be positive, then you can't be concave down anymore, which means you have to be concave up. You have to look like part of this, which means that you can only look at that side, because you have to be increasing and concave up, which means you have to look like that. Now that would grow without bound. That makes sense?
But wouldn't it start like this?
What? No, it doesn't start like this. We're going to do more of this. When you determine concavity, you're going to look like one side or the other. Okay? So if your function is increasing from the first derivative, you're going to look like the right side. If this was negative and this was positive, you would look like the left side. So it's going to be one or the other. We'll do more of that. I'm kind of getting ahead of myself. I'm just remembering that day sitting there blowing, I kind of blew his whole thing. Man, thanks a lot. So, yeah, well, I actually made him go think of, he got mad at me because I ruined it for him. And then I told him to go think about what condition we could add to it or something like that, and he got mad. He didn't fix it. That's probably why he's not here. But, all right. I want to do a trig function. We have 15 minutes. Let's see how far we can get with this. I'll tell you something else when Frank leaves. No. Same instructions as last time. Where's this thing going up? Where's it going down? So where is it increasing? Where is it decreasing? Find any local maximums and minimums. All right? Now this is a closed interval, right? So we could look for the absolute max and min, couldn't we? Hold on a second. We could look for the absolute max and min, but that's not what we're being asked to do. We're being asked to determine where it goes up and down, right? And then any local maxes and mins. So think about it this way. Let's say we had a function that did this. Right? That's kind of, I'm thinking of like, talk about a love function. Here's a past relationship, right? So it looks like this. It's like right there. There you go.
So are you saying that it was love at first sight
And then it just, it was a rocky relationship and then it ended. No, the point I was trying to make is take a look at this function right here. If I use the closed interval method, the only thing it's going to give me is the left endpoint and the right endpoint, right? What we're being asked here to do is to identify all of these places where we have these little undulations happening. So we have a lot more information to gather here. Does that make sense? Okay, so let's go and do this. First thing we do is the derivative. Don't tell Frank about that though. Oh, there he is. All right, so the derivative of this. Be real careful here. It's chain rule, right? What's the derivative of cosine squared x? So 2 comes out, cosine x times negative sine x. So we're done with that, right? Okay. 2 cosine x. So there's your first derivative. This is equal to, let me clean it up, negative 2 sine x cosine x minus 2 cosine x. That's a pretty nice derivative, right? Not too bad. I put the sine in front of the cosine, just force of habit, I guess. You could leave the cosine in front of the sine. What are we doing with this? Set it to 0, right? So set this thing equal to 0. Well, you need to draw on your pre-cal now. So in pre-cal, this is what we call a trigonometric equation, and we want to try and solve this. I heard move the 2 cosine x over,
Yeah,
but
so if you add 2 cosine to both sides, then you can divide out the negative 2 from both sides. You end up with sine.
hold on. Do you remember, did I ever tell you all about a problem like this and how to solve this? I feel like I have. No? Like to not divide both sides by x here? Maybe I haven't had this conversation with you. Solving this equation for x. Some people will say just divide both sides by x, and you get x is equal to what? 1, which is true, right? I mean, that is a solution to this equation. Agreed? But you're missing a solution. What solution are you missing?
Plus and minus.
No?
Would you not square root that originally?
0.
No? You're missing the solution 0, aren't you? And the reason you're missing it is because you divided by x. And when you divide by something, you're promising us it's not 0. So you actually you lost one of your solutions by doing this. So by moving the cosine to the other side and then dividing by cosine, you're going to lose solutions.
No, I'm not saying divide by cosine. I'm saying
Oh, I thought that's what you were saying to do.
if you add 2 cosine to both sides,
Uh-huh.
you'll get negative 2 sine x cosine x equals positive 2 cosine.
Uh-huh.
If you divide the negative 2 on the left-hand side by both sides, you'll cancel the 2's.
Yes.
And that's what I was saying.
Oh, I thought you said divide by cosine.
No.
Oh, okay. All right, in that case,
Yeah. So
it's
that way
fine.
You end up with sine x cosine x.
Equals cosine x. Okay, so then what would be the next step at that point?
You could technically divide, I'm going to go out on a limb here and say divide sine x, and then you have cosine equals.
You can't divide by something you can't control, though. That's the thing, that's the point I'm trying to make here. You don't ever want to divide both sides of an equation by something that has a variable expression in it, because then it could be something like 0 and you lose the solution. I think we're kind of overthinking it. What can you, look at the left side, just factor it. Just greatest common factor.
Well, you can back out
Negative 2 cosine x comes out. And then now you have sine x, what? We pulled the negative, so plus 1. Right? So we have that now? So now, this is just like when you factor quadratic, right? When you factor quadratic, you have these two factors, you set them both equal to 0. Okay, so now, I'm going to take negative 2 cosine x, set it to 0, and then I'm going to take the other equation, sine, or the other factor, and set it equal to 0. The first equation, I just divide both sides by negative 2, I get cosine x equals 0. So where is cosine x equal to 0? So where's your cosine function 0? And you're only allowed to look between 0 and 2 pi. Where is it? Cosine is back on the unit circle. Cosine is the x coordinate, right? So where is it 0? Here and here, right? So here this would happen at x equals pi over 2 and 3 pi over 2. Okay, this one is sine x equals negative 1. So on the unit circle, sine is the y coordinate, right? Right? So where is the y coordinate negative 1? Right here, right? Which is 3 pi over 2? Yes? Which we already have. So we only have two critical numbers. Got it? So far? Now I do need to check, is the derivative ever not exist? Yeah, the sine function, the cosine functions are defined everywhere, right? Think of the sine curve going in both directions for everywhere. So we definitely don't have any problems between 0 and 2 pi. So this doesn't happen. So now I do a number line. Okay, I have two critical numbers, and I'm going to draw them on the number line. I'm going to do it right here. So I'm going to draw my number line, and look at this. 0, 2 pi. I live in here, right? Nothing outside of here. And that's because the domain was given to me in the beginning. Okay, pi is in the middle. I'm just doing this for help. Pi over 2 is here. That's one of my critical numbers. And then 3 pi over 2 is here. and that's my second critical number. So I've got to pick test numbers, don't I? So what's the first test number you want me to use? Here? Something in there? Where are these going to get plugged in? When I get these test points, where are they going to get plugged in? To the derivative, right? And this is my derivative, which has trig stuff in it, right? So I better use some angles that I know.
30 degrees.
Something that is, we've got somewhere burned into our brains. I'm going to use pi over 4 because I know pi over 4 is less than pi over 2. And then that's one test point. And then look at this one right here, pi. I can grab pi, right? And then something over here.
30 degrees.
Which is what in radians? We use almost exclusive radians from here on out. Degrees comes up very seldom. What?
Is it an 11 pi over 6? Is that 300 degrees?
11 pi over 6 will work. That's not the only one, but there are different ones we could use as long as it's bigger than 3 pi over 2. Right? And now we get to plug those in to our derivative. So we get to plug in, what is f prime of pi over 4. Now check this out. Let's see if you can follow this. This is pretty awesome. Watch. Do you agree, yes or no, because I only have like 3 minutes. Do you agree that that's my derivative? It's this with the thing factored out. So I have multiplication right here. All right, is there anything that you can tell me about this right here? Right now, without even me telling you what x is. Pardon? What's the biggest that this could be? Okay, so if I do 1 plus 1, it's 2, right? What's the smallest this could be? -1, which would mean that we put it together as 0, right? Yes? So this piece right here will always have to be positive unless that thing becomes 0, right? But if this whole thing becomes 0, then I'm actually at one of my critical numbers, because that would make the whole derivative 0. So this always has to be positive, just by what I know about sign. This right here, well, this right here is a negative number. So all that really matters right now to us is this. What happens to the cosine part? Right? Do y'all follow that logic? So what's cosine of pi over 4? So where are you? Pi over 4 is in the first quadrant, right? Cosine is positive there, isn't it? Right? It's root 2 over 2. So I have a negative number times root 2 over 2, which is a positive number, times another positive number. That's all going to become negative. So this tells me my original function moves down here. What about at pi? So -2, cosine of pi, I'm at pi, right? Pointing that way. What's cosine of pi? Nope. Cosine of pi? -1. So this is negative times -1 times positive. So that's going to be positive. So it goes up. And then at 11 pi over 6, what is cosine at 11 pi over 6? Cosine is the x-coordinate, so positive. So I'll have a negative times a positive times a positive, that's negative. There we go. So my function is increasing between pi over 2 and 3 pi over 2. My function is decreasing between 0 and pi over 2 and 3 pi over 2 to 2 pi. Do I have a local max? Yes. Cosine x squared. What was the rest of it? -2 sine x. And I'm only looking between 0 and 2 pi. Oh. There it is. There's the graph, just so you see it. We found that there was a minimum at pi over 2. You can see it. We found that there was a maximum at 3 pi over 2, a local maximum at 3 pi over 2. We found that right there. Okay? All right. I'm thinking we'll probably do a quiz on Tuesday, because we said we were going to get back on to where you would have the weekend to prepare for the quiz. The quiz will be on 4.1 and 4.2. So I'm not 4.1 and 4.2, 4.1 and 4.3. So 4.1 is what we did last time. Why are we not doing it? We're going to bring it we're going to do it at the end. It doesn't need to be here. We don't need it for anything we're doing. Okay? So do your homework. There's a lot of problems in the homework that are very different than anything I've done on the board. So you want to make sure you're doing those, watching my solution videos, all right? Because I expect that you can handle that algebra. Have a good weekend. Let me get my camera off real quick. Let me get my camera off real quick.